Okay, Assalamualaikum. I would like to explain the next secondary effect, which is the last one that we'll be learning in this course, which is called the Kirk effect. Kirk effect. So what is it? If you watch the previous video, so this is a graph of the gain versus the collector current of a BJT. So ideally, this graph should be a constant like this, so regardless of the value of the collector current, the gain will stay constant. However, it is not ideal at very low collector current. You can see the value of the beta, the gain is less than what it should be, and we already explained it. And for at high collector current, okay, this area is supposed to be constant, but now at very high collector current, the gain reduces, and this gain reduces what we call the Kirk effect. Okay, now I will explain how does Kirk effect happens and why does it happen. So once we understand why it happen, we can do clever designs and tricks to ensure that it will not happen. Okay, Kirk effect. So in the slides, you can read the slides, but as I mentioned, you couldn't rely 100% on the slides because it's very difficult to understand. So Kirk effect is one of the most complicated secondary effects. So you may watch these videos a few times. And Kirk effect, it occurs at very high collector current, where you can see the current gain drops. So basically, if you read here, it says the effective collector doping decreases. Okay, so now we want to explain why or how is the effective collector doping decreases at high collector current. To explain this Kirk effect, so better to start with the drawing. So this is a drawing of the BJT. Right, so you have the emitter, you have, it doesn't look straight, so you need to make it straight. Okay, roughly. So you have the emitter, the base, the collector. I exaggerate a bit the region of the base. It's supposed to be smaller, just to illustrate this Kirk effect. Otherwise, it's too small for you to see. Okay, so that we have the emitter, the base, and the collector terminal. Okay, now we are saying the Kirk effect is occurring at very high collector current. Okay, now we understand before how the BJT works, right? In normal condition, the one that I explained how the BJT works is actually at what you call it, a normal condition, like moderate collector current. Okay, now at very high, as we see at very high collector current, you see the gain is actually dropping. Okay, what before that, let's recap what is gain. The current gain is IC over IB. Okay, IC over IB. Now if we see this, okay, how does it works? Basically, the emitter from the electrons will diffuse from the emitter to the base side. Some will combine, and some will be drifted and collected at the collector. Okay, good. Now, so before that, so let's say this is a NPN. Let me do it like this: emitter, base, collector. So let's say this is a NPN transistor. So it's a, you can see here there are, again, you can see depletion region. So let me draw the depletion region over here. Okay, so let's say, so at the end side, so you are losing here, this side you are losing electrons, therefore you are left with positively charged ion. So let's draw that. And again, because it has to follow the space charge neutrality theory, so the other side will also have ion when it combines, and it must be the same amount. So 1 2 3 4 5 6 7 1 2 3 4 5 So 1, 2, 3, 4. Oh, maybe I should draw it. Wait a second. Like 5 as well. 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay. So this is how it looks like. So I will not draw the depletion of region over here because it doesn't concern us. The Kirk effect mostly happening in this area. Okay, that's the Kirk effect. Now, so as we understand again, how does it work? The electron will diffuse from the emitter to the base, and some will be drifted away. Okay, for normal condition, when the electrons, color do I want to make? Let's have orange. When the electron diffuses through the base and then being drifted to go to the collector side, right? So for normal or moderate collector current, these electrons that is drifted to go to the other side is not much, so it's okay. So nothing happened to the depletion region over here. The concern now is at very high collector current. At very high collector current, it means that if the collector current is high, it means that the emitter current is also very high, because as we know, the collector current, the source of the current is coming from the emitter side. So it means that the number of electrons that will be diffusing through the base and then drifted to the collector side over here will also be high. So now we are our station at very high collector current. So it means that this electron, we have a lot of electrons going through, a lot, too many. So what happens is, when the electrons passing through here, the depletion region, and especially on this area, as if you understand, right? This ionized atom is positively charged because it's losing the free carriers of electron. But when you have a lot of electron over here, right, at one time, some will be drifting in the same time, but due to the a lot of amount of the electron over here, you will see as if this this ionized atom over here, it looks like this ionized atom is getting back the free electron. So each one will get, so maybe not one, but not all, but then suddenly as if some of the ionized atom, the positive ion over here, will gain free electron. So what happens if that happens? It means that you are losing ion. Ion is when you lose free carrier, but now the ions is getting the free carriers again. So now we are losing maybe, let's say, 2 or 3 of the positive atom. So if that's the case, when the positive atom become less because of this huge amount of carriers going through it, so I can redraw this depletion region. So which means that the depletion region will become smaller, right? Because the number of the numbers of ions are decreasing. So again, space charge neutrality is there. Therefore, if now 1, 2, 3, 4, 5, 6, 7, you only have 7 positive ions. So therefore, this side also we need to have only 7. So we have to, because in the end it will try to retain the space charge neutrality. So we deduct 3 over here as well. So you can see the total amount of ionized atom or the ion less. Therefore, we can redraw this depletion region thickness. So let me draw it like this. Okay, because let me redraw it here, something like that. Okay, so what happens is, again, so to sum up, so this, when you have a lot of electron going through here at high collector current, you reduce the number of atoms, therefore you reduce the amount, the depletion width at the collector side. In the end, it means the space charge neutrality means that it's also you are reducing the number of atoms this side and also reduce the depletion width. Okay, now what happens is, the previous depletion region was here. Okay, the blue one is the the old one. So now with very high collector current, we have the, let's not choose the same color. We have the purple. Yeah, okay. The previous one the blue, the new one is the purple. So you can see the reduction on the effective base width. So the whole region over here is the base, right? But once these are depleted, some region of the base are being depleted, the effective base width is the one that with no depletion. Okay, so with this very high collector current, you can see that the region of the effective base width becomes smaller, and so become bigger, because now the one that, okay, have I explained wrongly just now? So let me repeat just to make sure I didn't say anything wrong. The purple one is the one after at very high collector current. The blue one is at low or moderate collector current. Okay, so the new one is the purple one. So you can see, comparing this region here to the region of the blue is bigger. So it means that after at very high collector current, the effective base width increases. Effective base width increases. Okay, increases. So if this increases, as we explained before, you will understand what will happen. It will affect the recombination process. So remember, for BJT we try to make the base width as thin as possible to reduce the recombination. Why do we want to reduce the recombination? Because we want to reduce IB. If IB is small, beta will be high. Okay, it's inversely proportional. So we want to reduce the amount of recombination. So the probability to reduce the recombination is to make the effective base width smaller. Okay, smaller. But because of this Kirk effect, this effect whereby this effect is the reduction of the depletion width, reduction of the effective collector doping, therefore in the end reduces the depletion width. It has increases the base width, the effective base width, and therefore the recombination increases. So this Kirk effect is the process of inverse of the early effect. Early effect is when the depletion width become bigger, but in this the depletion width becomes smaller. Therefore, you have a bigger effective base width. Therefore, you have increased the recombination. So when the recombination increases, therefore IB will increase. So if IB increases over here, you can see here, right? This is the equation for the base, the current gain. So if the base increases, the base current increases, so this ratio will be different. Therefore, beta will decrease because it's inversely proportional. So therefore, in the end, that's why you will see in the graph that I will show later that the current decreases. No, the beta decreases with higher collector current. So so I'm showing again the graph of the current gain versus the collector current, and as you know, in the Kirk effect, what happened in the end, the beta decreases with increasing collector current. So the more collector current that you have, it will give therefore more of the reduction of the effective collector doping, which means that more depletion, you will lose more ions. Therefore the depletion region becomes smaller, the effective base region become bigger, and therefore higher recombination, therefore increases of the base current. So if the increased base current, it will affect the gain.